Alright guys, so I had a question about a problem that's not assigned for homework, but it's similar to something that's assigned for homework. It's on page 65. Let's see, I have the ebook pulled up. So it's this problem right here, page 65. It's actually not even numbered, it's just an exploration. But it's something we've talked about, and there's homework like this. So it says the following points lie on the graph of f of x equals x squared. You have point P is the point 1, comma 1. And then what you're doing is you're taking points Q that have x values that are getting progressively closer and closer and closer to 1, the x value of 1. And what we want to do is look at the slopes of the secant lines of each of those. Again, this is exactly what we're going to do in Chapter 3 when we define a derivative. We're going to essentially take the limit as that distance between the x values gets smaller and smaller, and see that we can find the slope of the tangent line by getting essentially better and better approximations for the slope of a secant line. Okay, but we haven't learned calculus yet, so we're going to do algebra right now. So the question was, how can you kind of like visualize this, using an online graphing calculator? Now I'm going to use Desmos. It's free, it looks nice, it's fairly intuitive to use once you get used to it. Again, you can't use it on a test, obviously, but you certainly could use it while you're trying to do your homework. I wouldn't use it exclusively because you want to be familiar with your graphing calculator as well, but you could certainly use it for in addition to your TI 83 or 84 or whatever. So let's take a look. I'll be passing back and forth here. So let's see here. Let's first plot f of x and see what's going on. So go to Desmos. I have it pulled up here. Just go start graphing. First of all, we need to define a function. Since the textbook called it f of x, let's call it f of x. So f of x equals x squared. Of course, it's a parabola with the vertex at 0, 0. We all know that. So that makes sense. Okay. Let's see. What else? So the point P was 1, comma 1, right? So just type it in how you would, with the regular notation. 1, comma 1. So there is that point. If you want to get really fancy, you can do this. Instead of actually making that static, let's make it to where we can move it around. Say C, comma F of C. And it'll automatically say, hey, do you want to make that a variable you can move? And say, yeah. So now watch what I can do. Let's not show a label. See, I can move it around. Because the x value is always whatever you define as C, and it's f of C. So it's always going to be stuck on your parabola. And you can go here, and if you click on the endpoints of your interval, you can define it to be, go from -5 to +5, say, instead. Or let's say we want to be able to see it right here. So let's go -4 to 4. That way it will show on the screen. And we can say, make the step. That's as small as you can go. So it's not super small, but it works, I guess. You could even do this. So it's automatic, it bounces back and forth. Okay? Okay, other things you can do. You can set the scale over here. You can make it darker. I usually do this in class. Make it darker in projector mode. You can make the scale on the x-axis either smaller or larger, like we can count by ones on the scale, count by ones on x's and y's. We can turn off those kind of pesky minor axis grid lines if we want to. That might look a little better maybe. But there we go. All right, so let's put it there at 1, comma 1. Okay. So what we want to do here is we want to plot, and actually let's call that point P. That's nice. Okay, what we want to do now is plot points Q1, Q2, Q3, Q4, Q5 according to this right here. Okay, I could make a dynamic abstract formulation and then use that like a slider to move Q back and forth, but let's, for the time being, let's be static. Okay, so let's see here. Let's just plot these points. So we want to plot Q1 is 1.5 comma f of 1.5. So let's go over here and add a point. So we're going to say 1.5 comma f of 1.5. And there's the point. Let's label it Q1. Okay. Let's pick another point. Now let's zoom in because these are going to get on top of each other pretty soon here. The other point was, let's see, it was 1.1 comma 1.1. So now we see the pattern, 1.01 comma f of that value, 1.001. Okay, so let's plot these points. So 1.1 comma f of 1.1. Two parentheses, let's label that as Q2. Okay, then let's do the next point. That was 1.01 comma f of 1.01. That was Q3. Now we're gonna have to zoom in, or those are gonna be on top of each other. See here, they're gonna get really close really fast. So this is gonna get really jumbled up, but it's fine. Okay, what about 1.01 comma 001 comma f of 1.001. That is Q4. Again, we're getting so close, it's going to be hard to differentiate, but we can zoom in. See, we're zooming in really close here. I mean, look how close those points are. They're less than a hundredth or whatever we are away. Let's look at the scale. Yeah, less than a hundredth away. Okay, of course. I mean, look at how close the x values are, and of course the y values are going to be really close. And the last one is 1.0001 comma f of 1.0001. Okay, we can label that Q5. Okay. Now notice, I mean, we have to zoom in super to get there. Okay, look how close that is. I mean, super close there. Those y values are so close. Okay, I mean, if we zoom out, these are going to be way on top of each other, but we can still graph the lines, the secant lines. So the point here is that we want a secant line through P, Q1, PQ2, PQ3, PQ4, PQ5. Okay, so essentially P through all of these points. So that's going to be 1, 2, 3, 4, 5 lines, 5 secant lines. And the idea is that this one, PQ1, it's not going to be a very good approximation of the tangent line of f of x at 1. This secant line, say PQ2, will be decent. And as you keep getting PQ3, PQ4, then PQ5, PQ5 is going to be a pretty good approximation of the tangent line. Okay, now here's the question: how do I graph all these? Okay, well, I mean, you graph these by just using algebra. Okay, now I could like over here, I played around a few minutes ago. Essentially made a variable. I wrote a few expressions here and made it to where I can move the value of c and have a dynamic situation. So see here, I'm moving, essentially I'm moving the x value closer and closer and closer to 1 from the right, and those secant lines are getting to be a better and better approximation of the tangent line. Okay, so that blue line, that's a secant line, and it's almost looking like a tangent line of f of x, that's x squared, at the point x equal 1. As I get closer and closer, it actually equals. Now, if right here, that's when the tangent line actually would equal, would be there, but since how the function is defined, it goes away because it's undefined. Okay, that's no big deal. Okay, it's calculus, we'll get it exactly. All right. So now let's go back to where we were. We want to write it. We want to write just regular old, nothing dynamic here. We just want to write the equation that passes through the point 1, 1. That's p. Remember this right here, p. Let's make it not dynamic. Let's go over here and say, let's go here and just put 1, 1. There's p. Nothing dynamic. We're not going to change anything. Nothing fancy. There's 1. So we want to find the secant line PQ1. So we have 1, 1 and 1.5, 1.5. Now how do you do this? This is just straight up algebra. Here, I'll write down the formulas. Here's what you need. You need a slope formula. You need to find the slope between this point of the line, between this point and that point. Remember, that's y2 minus y1 divided by x2 minus x1. Once you have, so I'll break it apart into step 1. Once you have the slope formula, then you have you need to use point slope form. Step 2, use point slope form. Remember, what's point slope form? That's y minus y1 equals m times x minus x1. That's how you write the equation of a line that passes through 2 points. Okay, what can you do? You could let this be x1 comma y1. You'll have a slope from step 1. Then you'll have equation of a line. Now, we probably don't want to leave it in point slope form if we want to write the equation and graph it. We want to put it in slope intercept form. So that would be the next step. Let me write that down. Step 3 would be slope intercept form. So y equals mx plus b form. Okay. Once you put it in that form, then you can go down here and simply just type the equation in, y equals whatever, whatever, and the line will pop up. Okay, so let's do that. I'm going to use my calculator real fast since we have 5 to do here. But again, if you're doing it by hand, these are your steps. Find the slope of the line using p and say q1. Okay, now f of 1.5, that's just a number. If you want a shortcut to find f of 1.5, here's a trick. If you're using Desmos, go down here, say you want to add an item, go to table, and let's say not y1, but let's change this. Let's say we want to find f of that value. Now all you have to do here is say f of, now you have to be of the correct subscript, x underscore 1. Okay, now if I type in, let's see, what do I want to find? I want like 1.5 is my first x value, then 1.1, 1.01, 1.001. This will calculate those values for us, 1.5. So there's f of 1.5, 1.1, 1.01, 1.001, 1.0001. So there are the those are the y values that go right here. And so if you wanted to, you could actually replace f of 1.5 with 2.25. Nothing would change over here because that is what f of 1.5 is. You could replace f of 1.1 with 1.21, again, because that's what f of 1.1 actually equals. I was just being lazy here and didn't want to calculate it out. Okay. Now you should be able, I think you should be able to use that. I mean, that's a pretty rounded answer, but it looks like, that's going to be fine. To 4 decimal places, that should be fine for calculating the slope. Okay, so essentially what we want to do is just use the slope formula with 1.5, 2.25, 1, comma 1. Now I'm going to use my calculator to go ahead and find the answer. I mean, I know how to use algebra. You probably need to practice. So I would actually suggest you probably really need to practice, most of you guys. So you go ahead and do it by hand. I've done this hundreds and hundreds of times, and we're making a video, so I'm going to do it by calculator real fast. Okay. Again, we want to find the equation of a line through 1, comma 1, and then 1.5, comma 2.25. Okay, so let me see real fast. I have a formula that a program I wrote in my calculator not too long ago. Let's see here. So 1, comma 1, and we said 1.5, comma what was it? 2.25 rather. So 2.25. Okay, so I get the equation of that secant line is y equals 2.5. Y equals 2.5x minus 1.5. Okay, so there is my first secant line. See, it's passing through Q1 way up there. And that would be, a not so great approximation of my tangent line. But it's a start. Okay? Now let's do the exact same thing, except now with P, comma Q2. So again, we have x1, y1 here, and then x2, y2. Use the slope formula, go back to your original steps, slope formula, point slope form, and then convert that to slope-intercept form, and then put it down here. So I'm going to use the same my same program I wrote a little while ago. So let's see. We said it was we said that was P is still the same. That's 1, comma 1, 1, 1, and then we said 1.1. We're using Q2 this time, which is 1.1, comma 1.21. Okay. The equation of that line is, let's see here, y equals 2.1 x minus 1.1. So there is a little bit better of a secant line. Okay, now if I zoom out too much, you can kind of see what's going on. So the orange was my, I'm going to turn these labels off because they are all in the way. Let's turn all those labels off. Let's leave maybe P, since that's what we're concerned with. Okay, so the orange line, that's my secant line PQ1. My purple line is the secant line PQ2. So the purple one, is passing through a point that's closer to P, so it's actually a better approximation of the tangent line. So it's a better approximation, so the slope of that secant line is closer to the slope of the curve at x equal 1. They're not the same, but similar. So let's do the exact same thing again. Same process. Slope formula, point slope form, slope intercept form. But this time we're going to use P and the even closer point. I believe this time we need to use 1.01. So again, I'm using my calculator real fast. Hopefully I don't run into rounding errors here. We'll see what happens. So let's see here. We have the point 1, comma 1, 1.01, comma 1.01. Oh yeah, I run into rounding error here. So I guess I'll have to do it the old-fashioned way. So I'm actually gonna, at this point, I'm gonna have to speed up the video. So I'm gonna go ahead and do by hand just the algebra real fast. I'm gonna fast forward. I'm going to just do slope formula, point slope, and then convert to slope intercept. Y equals mx plus. I'm gonna do it 3 times real fast. We'll come back and I'll graph those lines. Okay. Okay, guys, back. I just did those by hand real fast. Alrighty. So the next 1. You know, my calculator, the program I wrote, I had to write it to where it rounds. I wasn't conceiving doing these in really small numbers when I wrote the program. So, at any rate, the next one, this would be the point. Let's see here, or the secant line rather. P. This is what, the third one. So let's see, 1, 2, 3. So P times Q3 here. Okay. So 1 comma 1 through 1.01 f of 1.01. Okay, and that equation is y equals. Oh, let's see. I didn't write that out real fast too. Let me see. Hold on just half a sec. Okay, it's 2.01 x minus 1.01. Okay, so now we added a new black secant line. Okay, so the orange, purple, black, getting better and better approximations. You know, the slopes of these secant lines are getting better and better approximations to the slope of the curve at point P. So it appears the trend here is that the slope of this curve at the point x equals 1 is going to be 2, it looks like to me, because we're getting 2.5, 2.1, 2.01. Let's see what the next secant line equation looks like. Y equals, let's see, the next one was 2.001 x minus 1.001. So now we have a red line. Oh, that's not red. We already have red. Let's make it green. Okay. So that's an even better. Now notice how it's almost the same as that black line. Okay. So it's barely any different. So notice here, because look at the slope. The slopes are barely different. Okay. The last one was P comma Q5, which were these 2 points. Okay, the equation of that line is y equals 2.0001 x minus 1.0001. Notice how the blue line, the green line, and the black line are nearly identical. I mean, if you zoom out, you can't even tell there's extra lines there. Okay, they're just kind of jumbled up on top of each other. But notice here the trend in the slopes. This is what you're talking about with limits, the limit process. Okay, we are bringing the point Q closer and closer to the point P. And if you observe the slope of all those secant lines, it's getting closer and closer and closer to 2. If we move that point Q, like if we had a Q6 and it was even closer to P, that slope would be even closer to 2. It might be 2.00001. Okay, so this is a good exercise at what's going on here. You could also use a table to demonstrate how that slope is getting closer and closer to 2. Let's consider this. Here, I'm kind of thinking on the fly here. Let's create another table. Go to Add an Item and go to Table. Now, remember, actually, let me add a note here. Or let's actually go back to the book. If you scroll up here, remember this is the slope of our secant line. Okay, we have 2 points. We have the point C comma f of C, and we have the point Q, which is C plus delta x comma f of C plus delta x. So we're going to add a little bit to our x value and then evaluate that at f. That's our Q point, our point Q rather. Okay, and as we let delta x get smaller and smaller, that is, get closer and closer and closer, the point Q get closer and closer and closer to P, the slopes of our secant lines approximate the slope of our tangent line. Okay. Now we can actually write essentially an expression like this, and then use the table feature to calculate those different slopes. So let's see here. Let me think about this. If we go over here, let's actually add. Yeah, we need to add an expression here. So we need to add a function, and that function is essentially going to be this right here. Now we can't type delta x into that calculator, so we need to like use d for delta x. Okay, and 1 is our c value, right? So we can define m. So m of, let's just say for the time being x. Let's make sure this is right. M of x equals, okay, we need a fraction, so add a fraction just by the backslash. It's f of 1 plus d minus f of 1 divided by d. And guess what? Hey, do you want to add a slider? Yes, I do. Okay, now, delta is a small positive, is a distance. So distance needs to be positive. So we need, lowest this is going to be a 0. Oh, let's say it's like 2 is the highest, and then let's make the step as small as we can do it. Is 0.1 is as low as it's going to, 0.01 is as low as it's going to let me go. I don't think it'll let me do 0.001. Oh yeah, it will. Okay, good. Okay, cool. I thought it wasn't going to let me do that. Okay. Now let's see here. If I go over here and then define this as let's see, d underscore 1, and I can maybe say this is m, not m, m of d. Nope, not let me do that. I have to define. Actually, I gotta get rid of this. Sorry, they're not letting me define d in more than one spot, so that's fine. We'll leave that alone. And then m underscore d1. Okay. Now I can do things like here, like type in. Well, what if d is 0.01? Oh, too many variables. What's the problem here? Maybe do this, maybe do that. No, don't like that. Sorry, you don't understand this. Oh, don't like that either. Okay. Let's just not do D then. Oh, I know what the problem is here. That's M of D. D underscore 1, D underscore 1. There we go. All right, all better. Okay. So what we're doing here is showing you how the slope is changing. Now let's start a little higher. Let's say the slope, let's say the change is 0.5. Does that look familiar? 0.5, that's our first slope. What if the distance between your x values, what was our second x value? Our second x value is 1.1. What's delta x? Delta x is the distance between your two x values. So the delta x between P and Q, the difference between the x values, is 0.1, then 0.01, then 0.001, then 0.0001. And we can calculate really easy, just like on a TI, how the slopes are changing. See here? The slope of that tangent line, that is the slope of the curve at the point P, which is 1, 1, certainly appears to be trending towards 2. We're getting closer and closer to 2, guys. That's the whole point of these secant lines. Okay? Again, delta x, d here, delta x is the difference in your x values. So this would be the point the delta x in this situation, this would be 1, and then 1.5 would be the two x values. And then right here, the situation right here on the second row is the two x values would be 1 and 1.01. So the distance between your x values is 0.01. Okay. Again, this column here is the distances between the x values, and this column right here, I just have to calculate the slope of those secant lines, because this, again, is this right here. This is simply the slope formula. When you have two abstract points, you have the point C comma f of c, and you have the point c plus delta x comma f of c plus delta x. Write it out. This is essentially y2 minus y1 over, x2 minus x1. Simplify a little bit. Here you go. That's exactly what we have right here. Okay. Let's like delta x being smaller. 0.0000001. Nope. Let's add another 0. See, I mean, you can clearly see that in this situation, the slope of the curve at x equal 1 at point P is going to be 2. Okay, because the secant line slopes. Here's the first secant line slope, the second secant line slope, third, fourth, fifth, sixth. You can tell the slopes are getting closer and closer and closer to 2. Now here's the funny thing, super funny thing. With algebra, if I all of a sudden said, hey, let's move P, then we have to do this all over again with algebra. Because then you have to move Q, to where close to your new P value, and you have to do all those secant lines over and over again. It would be a pain in the butt. However, what we're going to do with calculus in chapter 3 is going to make this so easy. Okay? Well, I say so easy. It won't be easy to you at first. By the end of the semester, it'll be really easy. Okay? Finding the slope of a curve at a certain point will be second nature at that point. Okay? But right now, using algebra, it's a tedious process. We have to find all of these. Actually, let me turn that off, because that's not what we want. We want to calculate. We don't care about the line. So we have to calculate all these secant lines. You can't even tell the difference apart. Now, if you were on a TI, good luck at even like seeing the difference of these at all. Because on the TI, I don't know, they're great, but as far as like being really dynamic like this, they're kind of hard to deal with. But we can keep on zooming in. Things look nice and neat. Oh, I should turn those points off. These points right here are meaningless. Let's forget about those. Okay, well, they're not meaningless. I don't want them in this context. Okay, so again, if we zoom in, we can see all those different secant lines. We have to zoom in really far, though. Okay, so let's see. Orange, what do you have here? So red is the curve. No, red is one of the. Is red one of the secant lines? No. Okay, so red is the curve, and then we have the orange is the first secant line. It's the worst one. Purple was the second secant line. Then you had black. Then you had, let's zoom in even further. Then you had green. Then you had blue. Blue is the best estimate. The slope of the blue one was, let's see, 1, 2, 3, 4, 5. Was the fifth one here. So it was 1, 2, 3, 4, 5. It was 2.0001. Okay, pretty darn close to 2. Okay. So again, guys, I meant for this video to be a short video. It turned out being long. I hope it's been informative. But again, you can do a whole lot with Desmos. Okay, I did here. Everything was static. I tend to do everything more dynamic. Do everything in the abstract, so then I can move things around. For instance, I'll just pull up my other one that let's see. Let me sign in real fast. Okay. Let's see here. Here we go. I showed you guys this in class. But here's the dynamic one that I made. Okay, so you just go over here and you make the h smaller, so the purple is the tangent line. That's where the tangent line is the line that just barely touches, and at this point it's a equals 1, so just like we were working with previously. And at that point the slope of the tangent line is equal to the slope of the curve. Okay, and right there, that green line is the secant line, and it's not a very good approximation of the purple line. That is, the slopes aren't very close together. They're not too similar. I mean, they're similar. They're both positive, but they're not very, very similar. And let me see here. Let's make this point 0, 0, 0, 1. Oh, 1. Okay. As I keep... Why did it not do that? Oh well. Let me try that again. Let's see what's going on here. Yeah, why are you not doing like I asked? Okay. Well, oh well. Okay, so as I move that green point closer and closer to the purple point, that is, their x values are getting closer together, the slope of the green line gets more and more similar to the slope of the purple line. And again, the purple line, I don't have that yet. We don't get that till calculus, but that's what we want to try to approximate. Okay, that's why we're using the green lines to start with, the secant lines. And so the distance is 0.2 right now, then 0.1. So now, when delta x here is 0.1, they're pretty close together. Those slopes are pretty similar. Okay. All right, and I really want you to understand, this picture, because we're going to revisit this picture first thing in chapter 3. Okay, because we're going to essentially take the limit of a situation like this, and that's how we're going to find a derivative for the first time. We're going to take the limit as delta x goes to 0. That is, as the distance between your two x values goes to 0. And when you take the limit of that thing as it goes to 0, you get your derivative. That's essentially one way to take a derivative. Okay? So I really want you to really understand this. And if you have any questions at all, please let me know. I'll be more than happy to explain it again, or swing by my office. I'll be more than happy to explain it again, or we can talk about it in class some more. All right, you guys have a good one.